Hello gang, welcome back. We're going to do a little bit of review and we're going to talk about an approach that you might use to obtain the derivative of a trig function. And I know you've memorized some of those already, so you know what they are. I'm going to show you how you might get them, and also we'll have some further discussion of constant factors and why we can carry them through. I hope you didn't have any trouble showing that using the quotient rule to get this derivative. So hopefully that worked out okay. And you were able to work through that. So in terms of a basic review, remember what we're doing is remember what a derivative is. A derivative is basically the slope of a line evaluated at a point. So it's evaluated in the limit that the dx, or in a delta y delta x type computation, the dx goes to 0. So we're calculating slopes point by point, and we saw in this case that the result was that the derivative of the cosine, the slopes of the cosine function, are equal to the negative of the sine. So that was a fairly straightforward relationship, one easy to remember. The nice thing about having the derivative, knowing what the derivative is we don't have to go through this laborious method of computing the slope between 2 points on the curve at each point along the curve in order to get this. So we know what it is now. So what I wanted to do was look at the derivative of, a simple approach for obtaining the derivatives of trig function, something like the sine function here. Remember what the basic definition of the derivative is. We're taking, we're kind of evaluating in the limit that delta theta goes to 0, sine of theta plus delta theta minus sine of theta over delta theta. This would be like y plus dy, y plus delta y. So we have some basic identities that we can use to actually work through this. I mean, you know that the derivative of the sine of theta is equal to the cosine of theta. So what we want to do is just show how that comes about. So you'll remember these derivatives from your trig class, these identities rather from your trigonometry class. We see that the sine of theta plus delta theta is equal to the sine of theta, cosine delta theta, plus cosine theta, sine delta theta, and so on for cosine of theta minus delta theta, sine of theta minus delta theta, cosine of theta plus delta theta. So this is obviously the relationship that we want to use up here in determining what this derivative is. So we'll substitute sine of theta plus delta theta equal sine theta cosine delta theta plus cosine theta sine delta theta to get this ratio here. So sine theta cosine delta theta plus cosine theta sine delta theta minus sine of theta divided by delta theta. So at this point, when you're trying to work through something like this, you need to look at these terms and think about what's going to happen to these terms when, cosine of delta theta, sine of delta theta. When delta theta gets really small, when it goes to 0. Well, there are a couple obvious relationships to consider. Cosine of delta theta, when delta theta goes to 0, the cosine of delta theta is going to approach 1, right? And as delta theta approaches 0, sine of delta theta is also going to approach delta theta. But this second relationship, while true, doesn't really help us out too much because we'd end up with 0 over 0. We aren't really, we don't quite know what that means. So we're going to take a series expansion of sine of delta theta to see what that looks like when delta theta becomes really small. And what we find is that the sine of delta theta, using an expansion of terms there, is delta theta minus delta theta cubed over 3 factorial plus delta theta to the 5th over 5 factorial. So you see we have all the odd powers of delta theta cubed to the 5th, to the 7th, to the 9th, and so on over 3 factorial, 5, 7 factorial, and so on. Now, I think you know what happens, because we talked about this before. When delta theta is almost 0, then delta theta cubed, delta theta to the 5th, delta theta to the 7th are, well, if this is almost 0, this is certainly much closer to 0. So, and that's the point here in this expansion, is to show that sine of delta theta goes to delta theta. And although delta theta goes to 0, we aren't too comfortable with 0 over 0. So let's come back and look at this expression here. We have the sine of theta cosine delta theta plus cosine theta sine delta theta minus sine of theta over our delta theta. Sine of delta theta goes to delta theta. This cosine of delta theta goes to 1. So we end up with sine of theta times 1 plus cosine of theta times delta theta minus the sine of theta. So these are going to cancel out. We end up, in the limit that delta theta goes to 0, that these terms of these relationships up here become cosine of theta times delta theta. Now, delta theta over delta theta, no one would argue that's going to be equal to 1. So this is equal to the cosine of theta, which you probably already knew. Another way to say that is cosine of theta in the limit that sine of theta, delta theta, which is our sine of theta over delta theta up here. It's another way we could have written that. Goes to 1, actually. So that's kind of easy to see that this limit here becomes this, which is just 1. So we've taken advantage. We've just shown you how you might go about doing it for the derivative of the sine. You could do this for other trigonometric functions as well, kind of going back to those basic identities. Now we can also use kind of a geometrical construction in order to see this relationship. The series expansion, that is, if we look at it graphically here, we have the arc length relationship, which is delta s, which is the length of this arc over here, is equal to r, the radius of this circle, times delta theta, which is the angle subtended by the arc delta s. Now notice that delta s and this quantity a are almost equal to each other. So if we take a kind of a close-up view, so this is going to be a little bit longer than this, but we're looking, in the limit that delta theta goes to 0. So we have the sine of delta theta we can write as a over r, the side opposite over the hypotenuse. But in the limit that delta theta goes to 0, this is approximately delta s over r. Same thing, these two are approximately equal. But delta s is equal to r delta theta. And so delta s over r is just equal to r delta theta over r, which is equal to delta theta. So again, we can see that sine of delta theta just approximately equal to delta theta when delta theta is very small. Okay, so we also kind of wanted to come back to this discussion of the factor that we, when we have something like we have a product y is equal to a times x, we could use the product rule, right? We already know that the derivative of b with respect to x is going to be 0, so I've just kind of added that in here because we know what that is. We know it's going to fall out, it's going to go to 0. But if we do, if you did feel that you had to go through the product rule, well, it might be worth going through once, but in the future, and we've already kind of assumed that we don't have to. But this would be the way that it would work out. We've got y is equal to ax. We let a equal f, f prime equals 0, x equal g, g prime equal 1. Right? So the derivative of a is equal to 0. Derivative of a with respect to x. So this term drops out. And that's the key to understanding why we don't have to worry about it, basically. We don't have to apply the product rule because this term is 0, this term is 0, and we are just left with basically a dx dx. So we think about this term in here, a dx dx. But dx dx is just 1. So when we're differentiating something like y, when it's a straight line, we have y is equal to ax plus b. A is just the slope, right? A is the slope of this line. We're taking the derivative, which is the slope, right? And the slope doesn't vary. Regardless of what the intercept is, the slope of this line is always going to be the same. It's always going to be equal to a. It's always going to be equal to dy dx, which is a in this case. So that was another point I just wanted to come back to. It's a simple point, just summarized here in these 2 points. And derivative of a constant times a variable is just the derivative of the variable multiplied by the constant. And the constant in a function, regardless of their value, doesn't change the value of the derivative. So next time we're going to look at the derivative of exponential functions and take some time with that. So thanks for joining me. Hope this was helpful. If it was, you can always like this video.